On this slide, we talk about separatedness and Hausdorffness. These two concepts are closely related. We have seen before that most algebraic sets are not Hausdorff, and we want to replace this concept of Hausdorffness with separatedness. So let us quickly recall the definition of Hausdorffness. So first of all, we would need the notion of product topology, and if you do not know what product topology is, you should immediately refer a book or search Wikipedia. So here we will say a topological space T is Hausdorff. If and only if diagonal. So this diagonal is in T times T. So diagonal is precisely when both the elements are equal. So delta T is nothing but diagonal. So this is a subset of T times T, and we write it as T comma T because both elements are equal, just like the diagonal in a square. So the diagonal has to be closed in T times T, and this T times T has the product topology. So this product topology comes from the topological space T, and so now we make an important remark. Most algebraic sets are not Hausdorff. So this we have seen before. We have seen that open sets are huge, and therefore it is very difficult to have a non-empty intersection of open sets. So now let us give an example, a fundamental example, and see that so notice this is true. So Zariski topology on A2 is not product topology, and this is what we want to show. So we immediately have a problem even in the simplest case of A1 times A1. So if you take the Zariski topology, you have a problem. Your diagonal will not be closed. So let us see this. So you know the subsets or the algebraic sets of A1 are the entire space A1 or finite sets or empty set. So A1 times A1 will be made up of vertical lines and horizontal lines and a bunch of finite sets. So there is no other option, because A1 considered as an algebraic set just consists of either finite number of points or the entire space or null set. So if you take this small set U times V, it will be made up of horizontal and vertical lines. So if you draw a diagonal, then the diagonal will not be closed because it is not made up of horizontal and vertical lines. So we immediately have a failure. So in the simplest case, we cannot have a diagonal which is closed in the product topology. Because the diagonal has to be made up of now horizontal and vertical lines, which are subsets of A1 times A1, and the diagonal is not made up of horizontal and vertical lines. So we immediately have a failure of Hausdorffness in the simplest case of A1 times A1, and therefore we need to replace Hausdorffness with something more helpful. So therefore we introduce the concept of separatedness. So this is analog of Hausdorffness. We do nothing much. We just do not worry about product topology. We just worry about algebraic sets. So separatedness is an analog of Hausdorffness, and we write down a definition now. So an algebraic set, this is defined over some closed field K. It is separated if the diagonal is closed in T times T as an algebraic set. So we just replace the first definition completely down, but we forget about product topology and we just think closed in terms of algebraic set. So the diagonal has to be defined by a polynomial equation, as simple as that. So this will be clear when we do some examples. So we have to define the diagonal in terms of a polynomial equation. That is it. We do not worry about product topology, about the underlying sets and how they interact with each other. So things are actually much easier. Let us give an example. So P1 is separated. So this is this you can use even to show A1 is separated, and it will be clear as soon as the example is done. So first we have to consider the cover of P1. Now P1 is covered by two sets, U0 and U1. So let me write this down. P1 is covered by two sets, U0 and U1. So U0 is corresponding to the set where the first coordinate is non-zero, and U1 is corresponding to the set where second coordinate is non-zero. So U0 where first coordinate is non-zero. So you divide out by the first coordinate, you get something like y1 comma x. And U1 is a set where the second coordinate is non-zero. So you divide by the second coordinate, you get y comma 1. So now we want to show the diagonal is closed. So first we need to find P1 times P1. So you have U0 times U0 union U0 times U1 union U1 times U0 union U1 times U1. So we need to show the diagonal is closed. For all I and j. So let us see U0 comma U0. So U0 times U0 is easy. It is just x comma x. It lies in A1 times A1, and this is a closed set. This is just the diagonal x equals to y. So x equals to y. So both coordinates are equal. So this diagonal is the algebraic set. So U1 times U1 is the same. It is y comma y, again a diagonal. Both coordinates are equal, and diagonal is an algebraic set. Something like a line x equals to y, and you are done. So the case of u1 times u0 and u0 times u1 is the same. So we just treat u0 times u1. So this will be a closed set xy equals to 1, and we will be done. So we need to explain why it is xy equals to 1. So u0 times u1 and u1 times u0 is also an algebraic set defined by the polynomial equation xy equals to 1. So what do we want? We want u0 and u1 to be both same. Yeah, so for u0 and u1 to be the same, we cannot have x vanishing. Yeah, because on the second set, the second coordinate does not vanish, so you can divide by x. Yeah, so the only thing you need to notice here is you can divide out by x, because when both the coordinates are equal, then the second coordinate cannot vanish. Yeah, the diagonal u0 is equal to u1, and that is precisely what I have put. 1 by x is equal to y, and that gives the result. We now give an example of a non-separated algebraic set. So what we do is we take two copies of A1 and identify them together except at the origin. So we keep their origin separate and everything else is identified. So if we do that, what we get is a non-separated algebraic set, and once we draw the figure it would be clear. So you need to keep it in mind, if from a line you take a point out, it is no longer a algebraic set in A2. Yeah, so there is no polynomial which can build a line with just one point missing. So that is the fact we will use in proving that a line with two origins is a non-separated algebraic set over K. So you write X is this A1 union A1. Yeah, so you identify two copies of A1. Everywhere it is identified except at the origin. So let us draw this figure. So you have identified everything except the origin. So we have two origins which I am drawing in two different colors, green and orange, which corresponding to two different copies of A1. So other than origin, you have identified everything else. So write 0 here to know that this is origin. So we will show this is a non-separated algebraic set. So again we form x times x, a product. So the way it looks like is you take the delta, that is the diagonal, and take sets u0 and u1. Now these sets u0, u1, u0 corresponds to the copy of a1 which has a green dot over it, and u1 corresponds to the copy which has orange dot over it. So both u0 is a1 and u1 is also a1. u0 corresponds to green dot a1 and u1 corresponds to, say, orange dot a1. So you see, you have not identified the origin. So since you have not identified the origin, everything else is identified, but the origin is missing when you take delta, because in delta is x comma x, both are equal. So both are equal everywhere except at the origin, and that's why I have pointed a hole at the origin. So in A2, if you have a line or a curve with a hole in it, that cannot be the equation of a polynomial. Yeah, you cannot take a line and take a point out of it and say it is the equation of a polynomial. So 0 is missing. So since we cannot glue zeros together, we have that 0 missing, and because the 0 is missing from a single line, it is no longer the equation of a polynomial. So since it is not an equation of polynomial, diagonal is not closed. So notice that in A2, if the sets are like finite sets, the points, and then these irreducible curves. Yeah, so curves and points, the entire space and the null set are the algebraic sets in A2. So this we covered in the very first lecture. So we do not have like lines with hole missing as algebraic sets. For sake of completion, I have written U0 and U1, the copies which they correspond to. So now we just recall a bunch of definitions. Not recall, but rewrite or write for the first time. A variety over K is separated irreducible algebraic set over K. So 0-dimensional variety is a point, 1-dimensional variety is a curve, 2-dimensional variety is a surface, and 3-dimensional variety is threefold. Basically we are replacing Hausdorff with separatedness. So 1-dimensional variety is a curve, 2-dimensional variety is a surface, 3-dimensional variety is a threefold. So we want to now talk about compact sets. So the definition would be an algebraic set X is compact if X is separated. So let me write this down now. So we want to talk about compact sets. So algebraic set X is compact if X is separated and for every algebraic set Y every algebraic set Y and every closed subset so for every closed subset S, so S is a subset of X times Y, so the image of S in Y is closed in Y. So when you take the image of S in this algebraic set Y, it should be closed. So this will all be very clear once we discuss an example. So if the set is compact, you have to take another set Y, which is an algebraic set, form the product X times Y, then take a subset S which lies in X times Y, project it to Y and show that S is closed in Y. Yeah, and you start with the closed subset S. So that is how you show any space is compact. So example is A1 is not compact. Now first note that A1 is separated. Yeah, you can use the same diagonal argument as you used in the proof of showing P1 is separated. But A1 is not compact. Yeah, so we can use above definition. Yeah, instead of X we have A1, and we will take Y as A1 too. Yeah, because now Y is A1, Y is also an algebraic set, and we know X is separated. So the set S we will take as XY equals to 1. Now this is clearly a subset of A1 times A1, X times Y. So what do we need to check? We need to check that the image of S in Y is closed in Y. So in this case we have to check image of S in Y, which is A1, is A1 minus 0. So you know when you XY equals to 1, when you project it on the x-axis, you recover the entire x-axis except the origin. So just the projection of XY equals to 1 on the x-axis, you recover the entire x-axis except the origin. And you know A1 minus 0 is not closed. So A1 is not compact.